February 12, 1942, the French coastline stretches cold and desolate under overcast skies as German engineer Colonel Rudolf Schmetzer stands atop the chalk cliffs of Normandy, salt spray stinging his weathered face. In his leather-bound notebook, he sketches what will become the most ambitious defensive construction project in human history. Behind him, the first concrete mixers begin their relentless work, pouring the foundations of a fortress that will consume more resources than the Empire State Building, repeated across 2,400 miles of European coastline. The Atlantic Wall was born from fear. German High Command knew that somewhere along Europe's western edge, Allied forces would eventually launch their inevitable assault. But where? The coastline stretched impossibly far, from Norway's fjords to Spain's beaches. Traditional military thinking suggested concentrating defenses at obvious landing points, yet the Allies could strike anywhere along this vast frontier. Schmetzer understood the mathematical nightmare confronting his superiors. Defending every mile with troops would require millions of soldiers. Germany needed those men for the Eastern Front, where brutal winter battles consumed entire divisions. The solution had to be concrete and steel, not flesh and blood. The engineering challenge seemed insurmountable. How do you fortify 2,400 miles of diverse terrain? Rocky Norwegian cliffs demanded different approaches than Dutch sand dunes or French river estuaries. Each location presented unique problems of geology, tide patterns, and strategic importance. The construction would require more concrete than Germany had ever produced, more steel than its factories could easily spare, and a workforce that simply didn't exist. Enter Fritz Todt, the Third Reich's master builder. Todt had already demonstrated his engineering prowess with the Autobahn highway system, carving ribbons of concrete through German forests and mountains. Now he faced a project that dwarfed his previous achievements. The Atlantic Wall would demand revolutionary construction techniques, innovative bunker designs, and logistical coordination across occupied Europe. Todt's engineers began by studying the coastline with scientific precision. Teams of surveyors mapped every beach gradient, measured tidal ranges, and calculated fields of fire. They identified 15,000 individual strong points where fortifications would rise. Each position was plotted not just for its defensive value, but for how it connected to neighboring bunkers, creating interlocking zones of destruction that could shred attacking forces. The concrete requirements alone staggered military planners. Traditional fortifications used simple rectangular bunkers, but Todt's team designed curved aerodynamic structures that would deflect naval bombardment. These weren't mere concrete boxes, but sophisticated engineering marvels with walls 6 feet thick, reinforced with steel mesh that could absorb tremendous punishment. The curved surfaces followed mathematical principles borrowed from ship design, allowing explosive force to flow around the structures rather than through them. German engineers faced a steel crisis that threatened the entire project. The Wehrmacht needed steel for tanks, ships, and aircraft. Every ton allocated to bunkers meant fewer weapons for the front lines. Innovative solutions emerged from this constraint. Engineers developed new concrete formulations using locally available materials. Norman limestone was crushed and mixed with cement to create bunkers that blended into the coastal landscape. Belgian gravel provided aggregate for foundations that would anchor these fortresses against storms and shellfire. The labor shortage proved equally challenging. German construction workers were either fighting on distant battlefields or building aircraft factories in the homeland. Todt's organization turned to conscripted workers from across occupied Europe. French construction crews found themselves building fortifications against their own liberation. Dutch engineers applied their expertise in coastal engineering to projects designed to repel British forces. Italian stonemasons shaped embrasures for guns that would fire on American landing craft. These workers faced brutal conditions along the windswept coast. Winter construction in Norway meant pouring concrete in temperatures that could freeze the mixture before it hardened. Special heating systems warmed concrete as it cured, while workers labored in conditions that claimed thousands of lives. Summer brought different challenges. As concrete poured in, Mediterranean heat could crack before it properly set. The bunker designs themselves represented revolutionary thinking in fortification engineering. Traditional coastal forts placed heavy guns in obvious positions, making them easy targets for naval bombardment. German engineers developed camouflage positions that appeared as innocent coastal features until the moment of attack. Gun casements were built into artificial hills with narrow firing ports that provided maximum protection while maintaining deadly accuracy. Innovation extended to the smallest details. Ventilation systems used automotive fans to maintain airflow during gas attacks. Periscopes, borrowed from submarine technology, allowed defenders to observe approaching enemies without exposing themselves. Communication cables were buried in concrete conduits that could survive direct hits, maintaining contact between scattered strongpoints during the chaos of battle. The construction timeline demanded industrial-scale organization. Concrete plants were built specifically to supply the Atlantic Wall, with railway lines extending to the most remote construction sites. Specialized trains carried precast concrete sections that could be assembled quickly into bunkers and obstacles. German logistics officers coordinated this massive supply chain while under constant threat of Allied bombing raids targeting construction materials. As 1943 dawned, the Atlantic Wall began taking recognizable shape. Massive gun positions crowned strategic headlands, their reinforced concrete silhouettes changing the coastline's appearance. Tank barriers stretched across beaches where the geography favored armored landings. Millions of mines created invisible fields of death in the surf zones where landing craft would beach. Yet for all the concrete and steel being poured along the coast, the real engineering challenge lay beneath the surface. Major Ernst Hoffmann, a former mining engineer from the Ruhr Valley, understood that the Atlantic Wall's foundation systems would determine whether these massive structures could withstand the thunderous impact of naval bombardment. Standing in the muddy excavation that would become Bunker WN-72 near Omaha Beach, Hoffmann watched his crews drive steel pilings 30 feet into the Norman soil, creating anchor points that could distribute the crushing weight of reinforced concrete walls 8 feet thick. The mathematics of fortress construction demanded precision that few engineers had ever attempted. Each bunker required foundation calculations that accounted for soil compression, water table fluctuations, and the massive recoil forces generated by the heavy artillery pieces these structures would house. Hoffmann's teams used pneumatic hammers to drive foundation pilings through layers of sand, clay, and bedrock, creating root systems of steel that extended far deeper than the visible bunker walls. When completed, a single heavy gun emplacement rested on foundation work equivalent to a 10-story building turned upside down. The concrete mixture itself represented revolutionary engineering chemistry. German chemists developed specialized formulations that could cure properly in the harsh coastal environment where salt spray and freezing temperatures threatened to crack conventional concrete. They added volcanic ash imported from Italy, creating chemical reactions that made the concrete stronger over time rather than weaker. Some bunkers used aggregate made from crushed granite, trucked hundreds of miles from quarries in the Black Forest, because local sand and gravel couldn't provide the compression strength needed for walls designed to stop 16-inch naval shells. Construction crews worked around the clock in 12-hour shifts, their work illuminated by massive floodlights that made them targets for increasingly frequent Allied air raids. The night shift posed particular challenges, as workers poured concrete in darkness while listening for the drone of approaching bombers. Concrete work couldn't be interrupted once it began. A partially poured wall that set improperly would have to be demolished and rebuilt from scratch. The pressure to maintain construction schedules despite air attacks created an atmosphere of constant tension at construction sites from Holland to the Spanish border. The specialized equipment required for Atlantic Wall construction strained German manufacturing capacity. Concrete mixers designed for this project could produce continuously for 18 hours without mechanical failure, their engines cooled by seawater pumped directly from the ocean. Steam-powered cranes lifted precast concrete sections weighing 15 tons, positioning them with precision measured in inches, while coastal winds threatened to turn these massive components into deadly projectiles. Mobile concrete plants moved along the coast on specially built railway cars, allowing construction crews to produce fresh concrete at remote locations where traditional supply methods would have been impossible. Interior bunker design reflected lessons learned from the brutal urban warfare at Stalingrad and other Eastern Front battles. Captain Werner Bausch, an architect who had designed civilian bomb shelters before the war, applied his knowledge of blast protection to military fortifications. His innovations included curved interior walls that deflected explosion forces, ventilation systems that prevented gas attacks, and ammunition storage areas separated by multiple blast doors. Bunkers featured dedicated spaces for medical treatment, communications equipment, and food storage that would allow garrison troops to survive weeks of siege conditions. The ventilation engineering alone represented cutting-edge technology. Each major bunker required air filtration systems that could operate during chemical attacks while providing sufficient airflow for dozens of men working in confined spaces. Electric fans drew air through activated carbon filters and water-cooled chambers, creating positive air pressure that prevented toxic gases from seeping through cracks or doorways. Emergency hand-cranked ventilation systems provided backup airflow if electrical power failed during bombardment. Camouflage presented unexpected engineering challenges. Massive concrete structures couldn't simply be hidden, so German engineers developed techniques to make bunkers appear less threatening than they actually were. False walls made bunkers look smaller from aerial reconnaissance photographs. Fake windows and doors created the illusion of abandoned buildings rather than active military installations. Some positions were built to resemble seaside vacation houses, complete with decorative shutters and flower boxes that concealed machine gun ports. The logistics of supplying construction materials revealed the project's staggering scale. A single large bunker complex required more than 300 tons of concrete, 40 tons of steel reinforcement, and specialized components shipped from factories across occupied Europe. Railway schedules were coordinated to deliver construction materials while still maintaining the freight capacity needed for military supplies heading to other fronts. Coastal roads, many built centuries earlier for fishing villages, had to be reinforced to handle the constant traffic of cement trucks and material convoys. Quality control became increasingly difficult as construction accelerated through 1943. Inspector teams moved constantly along the coast, testing concrete strength with specialized drilling equipment and measuring wall thickness with ultrasonic devices. They discovered that rushed construction sometimes resulted in air pockets within concrete walls, creating weak points that could fail catastrophically under bombardment. Remedial work required drilling into completed structures and injecting high-pressure concrete to fill voids, a time-consuming process that further strained construction schedules. The human cost of this construction marathon extended beyond the obvious dangers of heavy machinery and air raids. Workers suffered from concrete burns caused by prolonged contact with wet cement, respiratory problems from concrete dust, and injuries from reinforcing steel that could slice through heavy gloves. Medical stations at major construction sites treated hundreds of injured workers each month, while specially trained concrete crews worked in rotating shifts to prevent exhaustion-related accidents. By autumn 1943, the Atlantic Wall had consumed more steel than the entire German submarine fleet, more concrete than all the Autobahn construction of the previous decade. The engineering achievement was undeniable, yet questions remained about whether static fortifications could truly halt a determined amphibious assault supported by overwhelming naval and air power. The winter of 1943 brought the Atlantic Wall's first serious test under combat conditions, though not from the expected Allied invasion. Captain Wilhelm Brauer, an artillery officer stationed at Battery Taut near Calais, watched through his periscope as British destroyers emerged from the morning fog on December 15th, their guns already trained on his massive concrete position. The thunderous exchange that followed would prove whether German engineering could withstand the crushing power of naval bombardment that engineers had calculated on paper but never experienced in reality. Battery Taut housed 4 enormous railway guns, each weighing over 200 tons and capable of hurling shells across the English Channel. The concrete casemate protecting these weapons measured 12 feet thick at its strongest points, reinforced with a steel mesh so dense that construction crews had nicknamed it iron wallpaper. As British shells began impacting the structure, Brauer felt the massive bunker shudder with each hit, concrete dust raining from the ceiling while his crew continued serving their guns. The battle lasted 4 hours, and when the smoke cleared, the battery remained operational, despite receiving over 30 direct hits from heavy naval artillery. This baptism by fire revealed both the strengths and critical weaknesses of Atlantic Wall engineering. While the concrete structures could indeed absorb tremendous punishment, the ventilation systems often failed under bombardment, filling bunkers with choking dust and gun smoke. Electrical systems proved vulnerable to the shock waves transmitted through solid concrete, causing lighting failures and communication breakdowns at the worst possible moments. Most troubling, the narrow firing embrasures that protected artillery pieces also limited their fields of fire, creating blind spots that attacking forces could exploit. German engineers responded with modifications that would define the Atlantic Wall's final configuration. Technical Sergeant Klaus Richter, an electrical specialist from Munich, developed shock-resistant wiring systems that used flexible conduits and redundant power supplies. His innovation spread along the entire defensive line as existing bunkers received retrofitted electrical systems designed to function even after suffering direct hits. Richter's crews worked through the harsh winter of 1943, crawling through cramped concrete passages to install upgraded communications equipment that could maintain contact between defensive positions during the chaos of battle. The engineering challenges multiplied as construction expanded into increasingly difficult terrain. Lieutenant Hans Müller, a civil engineer who had helped build Germany's pre-war Autobahn system, found himself supervising bunker construction on the treacherous cliffs of the Channel Islands, where solid rock lay just inches beneath the surface. Traditional excavation proved impossible, forcing Müller's crews to use controlled explosions to carve gun positions directly into living rock. The work proceeded at a glacial pace, with each blast requiring careful calculation to avoid damaging nearby completed structures or causing catastrophic rockfalls that could bury entire work crews. These island fortifications showcased German concrete engineering at its most ambitious. Gun casemates were literally carved into cliffsides, their concrete facades blending seamlessly with natural rock formations to create positions that were virtually invisible from the sea. The construction process demanded techniques borrowed from both mining and marine engineering, as crews had to account for saltwater infiltration and the constant erosion caused by Atlantic storms. Specialized concrete mixtures incorporated chemical additives designed to resist seawater corrosion, extending the operational life of these positions indefinitely. Meanwhile, along the flat beaches of Normandy and the Low Countries, a different type of engineering challenge emerged. Major Friedrich Weber, a hydraulic engineer from Hamburg, supervised the construction of underwater obstacles designed to destroy landing craft before they could reach the beaches. These steel and concrete barriers required precise placement in the tidal zones, where construction crews could only work during low tide windows that lasted mere hours. Weber's teams raced against time twice, daily mixing concrete in portable plants and pouring foundations while waves lapped at their boots. The complexity of these beach obstacles reflected sophisticated understanding of amphibious warfare tactics. Curved steel rails called hedgehogs were positioned to puncture landing craft hulls, while concrete pyramids topped with contact mines created fields of destruction in the surf zone. Each obstacle required individual concrete footings anchored deep enough to resist both tidal action and the massive explosions that would inevitably accompany any invasion attempt. The mathematics of placement followed carefully calculated patterns designed to channel attacking forces into predetermined killing zones covered by bunker-mounted artillery. Quality control became increasingly critical as construction accelerated through early 1944. Captain Otto Brenner, a materials engineer from the Krupp Steel Works, traveled constantly along the Atlantic Wall, checking concrete quality and steel reinforcement installation. His inspections revealed troubling variations in construction standards, particularly at remote sites where supervision was minimal. Some bunkers showed concrete that had been mixed improperly, creating structures that appeared solid but contained internal weaknesses that could prove catastrophic under bombardment. Brenner instituted standardized testing procedures that required concrete samples from every major pour to be laboratory tested for compression strength and chemical composition. These quality control measures slowed construction, but ensured that completed fortifications met the exacting standards required for structures that might face the concentrated firepower of entire Allied fleets. Mobile testing laboratories followed construction crews along the coast, analyzing concrete quality within hours of each pour to catch problems before they became permanent weaknesses. The final months before D-Day saw frantic efforts to complete the most critical defensive positions. Sergeant Major Heinrich Stolz, a construction foreman who had supervised civilian building projects across Germany before the war, pushed his crews through 16-hour workdays to finish the gun positions at Pointe du Hoc. These casemates required some of the thickest concrete walls on the entire Atlantic Wall. As intelligence indicated, the Allies considered these particular guns a high-priority target for both bombing and ground assault. Working under constant air attack, Stolz's crews developed techniques for rapid concrete repair that could restore damaged structures within hours of bombing raids. Pre-mixed concrete was stockpiled near critical positions, along with steel reinforcement materials and portable mixing equipment that could be deployed quickly to patch blast damage. These repair capabilities proved essential as Allied bombing intensified in the months preceding the invasion, with some positions suffering repeated attacks that tested both original construction quality and emergency repair procedures. The Atlantic Wall's completion represented an engineering achievement that consumed the resources of an entire industrial nation. Over 1.2 million tons of steel had been woven into concrete structures that stretched across 2,400 miles of coastline, creating fortress positions whose scale dwarfed ancient defensive works like Hadrian's Wall or the Great Wall of China. The human cost of this construction included injuries and casualties among hundreds of thousands of workers, while the economic impact diverted resources that might otherwise have supported frontline military operations. Yet the ultimate test of German concrete engineering would come not from naval bombardment or aerial attack, but from the determined infantry who would fight their way across the beaches and up the cliffs, where these massive structures stood sentinel. The engineers who designed these fortifications understood that concrete alone could not guarantee victory, but they had created defensive positions that would extract a terrible price from any army brave enough to challenge them directly. The morning of June 6, 1944, arrived with an eerie calm that belied the storm approaching the Norman coast. Lieutenant Klaus Weber, an observation officer stationed in Bunker WN-74, overlooking what Allied planners had designated Omaha Beach, adjusted his field glasses as the first gray shapes materialized through the dawn mist. The massive concrete structure around him represented 3 years of engineering ambition, its walls thick enough to stop armor-piercing shells, its foundation anchored deep enough to survive earthquakes. Yet, as Weber counted the approaching Allied vessels, he realized he was witnessing not just a military assault, but the ultimate test of every calculation, every blueprint, every ton of concrete that German engineers had poured into their Atlantic fortress. The bombardment began at 0550 hours. Allied naval guns, some firing shells weighing over a ton, hammered the concrete positions with methodical precision. Weber felt each impact through the solid rock beneath his feet as the bunker's structure absorbed punishment that would have leveled city blocks. The engineering specifications that had seemed excessive during construction now proved their worth, as layer upon layer of reinforced concrete deflected direct hits that lit up the dawn sky with fountains of pulverized stone and twisted steel. The bunker's ventilation system, designed by specialists who had studied gas attacks from the previous war, filtered out the choking dust and cordite smoke that would otherwise have suffocated the defenders. Emergency lighting flickered on automatically when the main electrical systems failed, powered by generators buried so deep that even the heaviest shells couldn't reach them. Communication cables, protected within concrete conduits, maintained contact between defensive positions despite the overwhelming bombardment that severed surface telephone lines within minutes. As Allied infantry began their desperate charge up the beaches, Weber witnessed the deadly effectiveness of interlocking fields of fire that engineers had calculated with mathematical precision. Machine gun positions, built into the concrete at angles that maximized coverage while minimizing exposure, created overlapping zones of destruction that turned the beach approaches into killing fields. The concrete embrasures, shaped to deflect incoming fire while allowing unrestricted outgoing fire, demonstrated how engineering principles could multiply the effectiveness of individual weapons. Yet the Atlantic Wall's greatest test came not from direct assault, but from the innovative tactics that Allied forces developed to overcome seemingly impregnable positions. Combat engineers used explosive charges, flamethrowers, and specialized demolition equipment to methodically reduce concrete strongpoints that conventional weapons couldn't penetrate. Some bunkers fell to attacks from unexpected angles, revealing blind spots that designers had failed to anticipate. Others succumbed to sustained assault that overwhelmed their limited garrisons, proving that engineering alone couldn't substitute for adequate manpower. The aftermath of D-Day revealed both the strengths and limitations of fortress engineering on an unprecedented scale. Many concrete positions had survived direct hits from the heaviest Allied weapons, their reinforced structures intact even after their defenders had been forced to withdraw. Others showed catastrophic damage, where innovative Allied tactics had exploited engineering weaknesses, particularly in positions where construction shortcuts had compromised structural integrity. Military engineers from both sides studied the battlefield results with intense interest. The performance data gathered from the Atlantic Wall's combat test would influence defensive engineering for generations, from the concrete bunkers built during the Cold War to the hardened aircraft shelters that protect modern air forces. The lessons learned about foundation design, structural reinforcement, and ventilation systems under combat conditions became standard references in military engineering schools worldwide. The concrete legacy of the Atlantic Wall extends far beyond its original military purpose. Today, many of these structures serve as museums and historical monuments, their massive walls now hosting educational exhibits rather than artillery pieces. The Batterie de Longue-sur-Mer, where German engineers had mounted naval guns capable of engaging ships 20 miles offshore, now welcomes thousands of visitors who marvel at the precision of concrete work that has survived 80 years of Norman weather without significant deterioration. Marine biologists have discovered unexpected benefits from the Atlantic Wall's construction. The artificial reefs created by concrete obstacles and sunken bunkers now support thriving ecosystems along the French coast. Fish populations have colonized the complex structures, while marine plants have transformed gun positions into underwater gardens that attract diving enthusiasts from around the world. The concrete that was designed to repel invasion now provides sanctuary for species that have adapted to these artificial environments. Coastal engineers studying erosion control have found valuable lessons in the Atlantic Wall's construction techniques. The massive concrete structures have withstood decades of storms that have reshaped the surrounding beaches, demonstrating foundation and anchoring methods that modern coastal protection projects have adapted for civilian use. Sea walls protecting modern harbors often incorporate design principles first tested in military bunkers, while offshore wind farms use foundation systems derived from techniques developed for coastal fortification. The construction methods pioneered during the Atlantic Wall project influenced post-war infrastructure development across Europe. Techniques for high-volume concrete production, steel reinforcement systems, and rapid construction under adverse conditions found immediate application in rebuilding bombed cities. The logistical systems developed to supply remote construction sites became models for major infrastructure projects, from highway construction to power plant development. Modern terrorism protection has borrowed extensively from Atlantic Wall engineering principles. Government buildings, embassies, and critical infrastructure facilities worldwide use blast-resistant design concepts that trace their lineage directly to bunker construction techniques developed between 1942 and 1944. The mathematics of explosive resistance, the principles of progressive collapse prevention, and the integration of defensive systems with architectural requirements all reflect lessons learned from concrete fortification under combat conditions. Archaeological techniques developed to study Atlantic Wall construction have revolutionized understanding of concrete technology under extreme conditions. Researchers using ground-penetrating radar, core sampling, and chemical analysis have mapped the internal structure of bunkers with precision that reveals construction sequences, material variations, and quality control measures. These studies provide insights into large-scale construction management that benefit modern megaprojects facing similar logistical challenges. Climate scientists have found unexpected research opportunities in the Atlantic Wall's concrete structures. The massive thermal mass of these buildings, combined with their exposure to marine environments, creates unique microclimates that researchers use to study long-term weather pattern changes along the European coast. Temperature and humidity data collected from bunker interiors provides baseline measurements that help quantify coastal climate evolution over multiple decades. Educational institutions across Europe have developed programs that use Atlantic Wall sites to teach engineering, history, and environmental science in integrated curricula that demonstrate the long-term consequences of human construction activities. Students studying structural engineering examine concrete that has survived longer than most modern buildings, while history students confront the human stories embedded in these massive structures. The psychological impact of encountering these concrete monuments continues to influence visitors decades after their military purpose ended. The scale of the construction effort, visible in every massive wall and precisely shaped embrasure, provides tangible evidence of the industrial resources that 20th century warfare could mobilize. Standing within these structures, visitors experience the weight of history in the most literal sense, surrounded by thousands of tons of concrete that represent human ambition, fear, and engineering determination frozen in stone. Contemporary artists and filmmakers have found inspiration in the stark geometries and imposing scale of Atlantic Wall architecture. The clean lines and massive proportions that resulted from purely functional design requirements have influenced modern architectural movements, while the haunting atmosphere of abandoned fortifications provides settings for works exploring themes of conflict, memory, and the relationship between human construction and natural environment. The engineering legacy of the Atlantic Wall reminds us that ambitious construction projects leave permanent marks on both landscape and human understanding that extend far beyond their original purposes. These concrete structures, born from military necessity and engineering ambition, continue to serve, protect, and inspire in ways their creators never imagined. They stand as monuments not just to a specific moment in history, but to the enduring power of human engineering to reshape both the physical world and our understanding of what determined effort can accomplish even under the most challenging circumstances imaginable.